So thanks for coming back. Let's just have a quick chat about computational thinking, again, from a different perspective. All right, so in this set of notes, I've taken this from the reading. When I say the reading, there's a recommended textbook. It's not a textbook, it's a recommended reading book. Yeah, anyway, so they've got some chapters that are useful to this. I mentioned Wing. So these people here, Wing, and there's a few others actually, made some definitions of what computational thinking is. And so you've heard this a few times now. You got a solution that can be executed on a computer, that it can be automated. Other people have said that computational thinking is a mental orientation, or in other words, it's a way of thinking which is different than other ways of thinking. And so it's a way of thinking where we think about inputs, outputs, and processing. I'm sure that's familiar, right? So we think about what inputs we need, what processes we need to get what output. So output is going to be what we want to trade. And there may include some mathematics in it because it will have algorithms. And many algorithms are mathematical, which is probably why we see a lot of people who are mathematicians turn up in IT. So that happens a lot. These things are called the core concepts of computational thinking. In other words, according to the text, the book, these things here must be there. And there's some other things that you could add to them, but these things there are the minimum that you must have to say that you're doing computational thinking. So you must have logical thinking, which we're going to spend a bit of time on now. Deduction and induction and true and false Boolean. You must have algorithms step by step. Now, you remember in the previous slide, he broke it down into 4 things. Here we've got 7. So those 4 things that he mentioned are here too, I think. He had algorithm, decomposition, and abstraction, but we add to that modeling. Modeling is kind of related to abstraction, right? Generalization and pattern recognition. All those things were mentioned there, but we've added a few more to it, including evaluation. Evaluation is kind of added later. The idea being that we have to know at the end. Remember the scientific method? And we have to know at the end if what we've done has achieved our goal. So that's our evaluation there. So I mentioned that we must be logical. So it would be good to know about logic. Logic is not a new idea. The Greek people spent a lot of time sort of working out rules of logic. When I say the Greek people, I mean, I don't mean people living in Athens now. I mean the ancient Greek people 2,000 years ago. Spent a lot of time sort of coming up with that. And so that's why I've got a couple of examples there that are kind of like that. So we've got deductive, inductive, which are different. Deductive is really good for us as computing people because deductive translates almost directly into computer work, because computers can do deductive really nicely. Inductive, that's more like how we work. You know, on our daily day, working with the world, working with other people, we do a lot of inductive, which is a little bit more fuzzy, a little bit less certain. So there's working with uncertainty, working with probability. That would be where we'd be using induction. Boolean, that's computer. Again, that's going to be just like deductive. You know, it's true or it's false. So I hope you see the sort of tension that we have. We have the real world that we live in, where we have probabilities, we have uncertainties, and we need to get that, and that's where our problems are. We have to solve those problems with computers. Computers just work with true and false. You know what I mean? And that's why they can do deduction, because deduction is, you know, this is true, so that's true. Or this is true, and this is true, so that's false. You know, that kind of thing is, that's easy for a computer to do. It's not bad for us to do, but that's not the way most of the problems in the world are. And so we have to sort of come up with some intelligent way of sort of doing that. So let's go and start with this basic logic stuff. And we have these things called premises. I don't know if you've heard of those, premises and conclusions. If you take your premises and your conclusions and you put them together, you get an argument. So here's an example of an argument. An argument could be that Socrates is a man, all men are mortal, therefore Socrates is mortal. This is deduction. And that's basically, these two things are true, so that thing follows. And it's true. This is a valid argument. You put those things together. Now, what is happening in this valid argument is we have some premises which are true, they're strong, and our conclusion relates to the premises. And the logic is true. So this is a good argument. It's a strong argument. And that often happens in deductive reasoning. Okay, now here's somebody doing some deductive reasoning, but they have a failed argument. So Missy is a cow. All cows are brown. So Missy's brown. Well, there's a problem in that, right? And I hope that you can see it straight away. The problem is one of the premises is false. So if you have a false premise, probably your argument's going to be weak, and maybe you're going to have a failed argument. Missy might be brown. That's possible, but you can't say for sure that Missy's brown just because a lot of cows are brown. And that was the problem, was that. All right, so here's another one. Tennis balls are round. All tennis balls are round, correct? The Earth is round, so the Earth is a tennis ball. Now, it's faulty logic, right? So again, we can have faulty logic, or we can have faulty principles, but in either of those cases, we get a failed argument. Now, inductive reasoning is going to be a little bit different. In inductive reasoning, it's more real world. It's working with probabilities. It's working with uncertainty. You have 100 balls, 99 of them are red, 1 is black. All of those balls are taken by 100 people. Sarah is one of those 100 people. So could you say that Sarah has a red ball? You could say she probably has a red ball. And if you're a mathematician, you could say there's a 99% chance she has a red ball. Or yeah, that's how it is. We can assign a probability to it. That's induction, but we can't deductively say that she definitely has a red ball. So when we're doing our reasoning and our logic, there's some things that we have to do. We have to check that our reasoning is valid. I gave you a couple of examples of valid and invalid reasoning. We have to check that our input is reliable. Those could be the premises coming, all right? And then we're aware of that. Then we need to know, for this particular problem, do I need to do some kind of induction? No, which is going to be some uncertainty, or is it something follows directly? Can I do deduction, which is going to be your typical sort of straight from a algorithm, from a flow chart into some code, that might be sort of mathematical. I don't know if you've heard of Boolean. Boolean is true, false. That's basically the nuts and bolts of our computing. It's really, as it says there, unambiguous. Unambiguous. The word ambiguous means that you have. Yeah, well, don't listen then. I hate it when my phone does that. I lost my train of thought there, right? Ambiguous. So we want to be not ambiguous. Ambiguous is when one certain thing is a fact that could mean more than one thing. That's what we mean by ambiguous. I don't know what time I'm finishing today, right? I can't say that I'm going to finish at 5 o'clock. It's kind of ambiguous, right? So if you see somebody in a distance in a car, is that a man or a woman driving that car? It's a person, but beyond that, because they're 300 meters away, I can't really tell. And so that's ambiguous. If it was important to a computer program, whether it was a man or a woman, and the only input that I had was, yeah, there's definitely a person in that car, that would be a problem. You with me? We can have compound propositions. What that means is we can string propositions together using conjunctions or disjunctions. and we talk about those in a minute. So our conjunctions are using and statements, where we put two propositions together to make a bigger one, right? And, or we can use or. And, oh, I got to do it that way. So here's some of the logical operators that we can use. We can use and, or, not. Implies, which is just an arrow going in one direction, or if and only if, which is an arrow going in two directions. And I think I mentioned these in a previous lesson, correct? Don't remember? All right, so if something is true and it's true if and only if some other condition is happened, it means that, yeah, everything has to be for the, well, there's two things that it means. Yeah, it means absolutely this cannot be true unless that other thing is true. But it also means that it can go in the other direction. If and only if works in two directions, whereas implies only works in one direction. Yeah. So conjunction is and. What that means is this state here where P and Q are both true will exist when P is true and Q is true. But if either of those is false, like in these two cases, in this case Q is false, in this case P is false, then P and Q will have to be false. And if both of them are false, then P and Q will have to be false. All right, so that's conjunction. Computers work with zeros and ones. So what this means here is, look, if P is true, and that we use a 1 for true and a 0 for false. If P is 1 and Q is 1, then P and Q together will be 1. Every other case, it's not. Because if either of these is a 0, then this has to be a 0. It can't be true. Now, the opposite of that is our or statement. If either of these is true, if either P or Q is true, then the state of P or Q being true will be true. The only time it's not true is when they're both not true. Okay. The idea here is that if this and this, then that. Yeah. So that's not going to work in that case. It only works. Okay. So if these and this are the same, then that. Yeah. That's the imply. If P is false, then it implies that Q is false. Negation just reverses or inverts. If something was true and you negate it, then it's false. If something was false and you negate it, then it's true. True. So you can turn a false into a true by negating it. So if something is false and you negate it, it becomes true. And obviously, if something's true and you negate it, it becomes false. The if and only if. So if and only if Q, so this is Q, if and only if P. So if P is true, then Q will be true. If P is true, but Q is false, then it can't be true. So yeah, this only works in one direction. But if they're both false, then if and only if this is false and that's false, then that's false. All right, so Venn diagrams, are you familiar with those? Conjunction is a small area. That's the area where both P and Q are true. That can only be where they're intersecting. Disjunction, which is when either of them are true, so that can include both of them. Implies is sort of one directional, so the Q is implied there. The not, isn't that cool? It's just the opposite of each other. So I went through that kind of quickly. This stuff here was in the previous lesson. Right? Algorithms, sequence, iteration, selection, and state. Remember the diagram, the model that was the turnstile? Remember the turnstile? It had a state, right? Either the turnstile was open or it was locked. Remember that? So that's what they mean by the state. You remember that? No? You don't remember that? Okay. When you go to get on the metro, there's a thing that stops you from going. Yeah, okay. When you pay, it opens. But then it closes again. That's the state. And so that's a dynamic model. So things change as you go. We need to use logic. I really went through logic very, very quickly. Sorry about that. But yeah, there we go. Algorithms are step by step. We need to use precision because computers don't work with ambiguity. But the real world's ambiguity, isn't it? But so we have to sort of develop models that strip away the stuff that is not actually needed. And that's where our abstraction comes in. Variables as a scratch pad, you will see things like X as a variable or whatever, I suppose. That's kind of a dumb name for a variable, but a variable is not like a variable in mathematics. In mathematics, we use X and X is equal to Y or something like that. That's not how it works in computing. X is a place where we store the value that we're going to use somewhere else. So it's just a little storage place, scratch pad, a place where we dump something for a while until we use it somewhere else. So it's very different than math. Computer won't figure out what's wrong. Computer won't use any common sense. And we have these rules of precedence. When you are doing some calculation with the computer, you remember BODMAS from high school? BODMAS? Brackets, orders.
BODMAS.
The other one's division, multiplication, addition, and subtraction, right? BODMAS, right? So that's the order if you don't have, but you don't have to remember all of that because you can just use brackets. They always come first. And so you can use brackets to order your calculations. That's kind of recommended. If you're sort of not too sure, just go ahead and use your brackets and that'll sort of sort things out. Wow, I went through that fast. I hope that wasn't too fast, but it's been a long lesson.